So now we're going to talk about polyprotic acids. So polyprotic acids have two or more ionizable protons. And these protons come off in succession. So one comes off, leaving an anion, and then another one comes off. And so as an example, we can look at, this is sulfurous acid. So H2SO3, it has two ionizable hydrogens. In the first step, one hydrogen ion comes off and we're left with the hydrogen sulfite ion. And this has a Ka value. And then that hydrogen sulfite ion can also act as an acid and lose a hydrogen ion. And then we have the sulfite ion, and this has its own Ka. This Ka is much smaller than the first one. So each step has its own ionization constant. The second one is always a lot smaller. One way to think about this is the first proton is leaving a neutral molecule. So this is neutral molecule. We've got a positively charged thing leaving that. That's relatively easy. Here we have a negative anion and a positive charge is leaving. It's going to be harder for it to leave, right? Because this is attracted to that anion. So here are some polyprotic acids and their ionization constants. So we've got sulfuric acid. This is a very common polyprotic acid. It is strong in its first ionization. So the first hydrogen ion comes off completely, and then the second one is weak. For the rest of these, they're going to show Kas for both steps, or all three for phosphoric and citric acids. Any questions? Not sure what else to say about that. There. So, finding the pH of polyprotic acid solutions. So the first Ka is a lot larger than the second or third, and so the amount of hydronium ion formed by that first step is much larger than that formed by the others. And then also the formation of hydronium ion in the first step inhibits formation of hydronium ion in the second step. Let's go back to this slide and look at that. Come on. So our first ionization here, we're losing a hydrogen ion. And this is in equilibrium. The second ionization is also in equilibrium. The hydrogen ions given off by that first one add to the concentration of hydrogen ion here and cause this equilibrium to shift to the left. So it actually inhibits the second one from leaving. So for most polyprotic acids, we can treat them as if the first step is the only one that contributes to the hydrogen ion concentration. A major exception is a dilute solution of sulfuric acid, where the first one does contribute the majority, but then we also have to consider the second one. So let's find the pH of a 0.050 molar H2CO3 solution, that's carbonic acid. And to save us time going back and forth between slides, I've looked up Ka1 and Ka2 for this acid. So to find the pH of this solution, we need to look at the acid and write its ionization equation. So here we've got the HCO3, and that ionizes to form H plus and HCO3 minus. 0.050 molar is the concentration of the carbonic acid. The initial concentration of hydrogen ion is basically 0, and the hydrogen carbonate ion is also 0. And then we can look at the change. So this is going to go down x and up x and up x. And at equilibrium, 0.050 minus x, x and x. So here we're looking at the first ionization. So Ka is 4.3 times 10 to the minus 7. And that should be equal to so we're using Ka1, 4.3 times 10 to the minus 7, and that's going to be equal to x squared over the quantity 0.050 minus x. We can do the x is small approximation, or we can do it on the solver. Somebody do it on the solver, and I'm going to do x is small. So that's what I got.
This is 1468.
1468. Yeah.
1464, 1.39.
Okay, but still, all very close. And I checked the percentage, and it's 0.3%. So x is small. So we'll just go with this one since it's what I've written. So that is, well, obviously that's x, but x represents the hydrogen ion concentration, right? So let's look at the second ionization and see what happens, just for grins. So the second ionization is I'm taking this anion, HCO3 minus, and seeing how this will act as an acid. To make hydrogen ion and carbonate ion. So what is my starting concentration of HCO3? It's X. So that's going to be, we'll call that 1.47 times 10 to the minus 4. What's my starting concentration of hydrogen ion? X again. So 1.47 times 10 to the minus 4. What's my starting concentration of carbonate? 0. X. Everything can't be X. That would be easy. So is this going to go to the right or to the left? It has to go to the right because there's no carbonate, so it can't come to the left. So this is going to be minus X, that's plus X, and this is plus X. So I've got 1.47 times 10 to the minus 4 minus X. And this is 1.47 times 10 to the minus 4 plus X and X. So this is the second ionization. So the K is 5.6 times 10 to the minus 11. And this is going to equal these guys. Divided by this guy. Now that's a very small Ka value, right? 10 to the 11 minus 11. So I'm going to try X is small. Here X is small makes this much easier because if you get rid of the X's, then these also get crossed out. And X is equal to Ka. So here we have X being 5.6 times 10 to the minus 11. And that's going to equal, that's the carbonate concentration. But do we care about that? No, we're interested in the hydrogen ion concentration. What's the hydrogen ion concentration?
That number plus 1.47.
Yeah, it's this guy right here. So 1.47 times 10 to the minus 4 plus 5.6 times 10 to the minus 11. What do we get? Okay, I'll do it. 1.47.
You always redo it anyways, so it's like.
Well, it's good to have multiple people doing it. Actually, the truth is, when you say the numbers, I can't track and write them down, so I have to look at it. So, yeah, so I do the math, and it gives me this. So I added 5.6 times 10 to the minus 11, and it made no difference, right? Because this is so tiny, right? So did we need to look at this second ice table? Nope, didn't make any difference.
And it's just because it was, and can you know that by just looking at it, that you won't have to calculate it?
Yeah, almost always the second ionization is not going to be significant. The big exception is dilute solutions of sulfuric acid. So in calculating the pH of this solution, I can consider just the first ionization. So I'm going to look at this hydrogen ion concentration. Still haven't answered the actual question, which is what's the pH? So pH is the negative log of that. .83. Any questions?
So, if it doesn't change at all, we can just basically, it could be more.
Yeah. It's usually not going to have an effect for two reasons. First of all, this Ka is always going to be much smaller. That's 10,000 times smaller, right? That's a big difference. And then when we look at this equilibrium, we have the hydrogen ions that were released from the first ionization in the products, and that reduces the amount of ionization that will happen. So you take an already small ionization and you make it even smaller, and it just really doesn't matter almost all the time. Any questions?
And I'm assuming the second ionization cannot be bigger.
The second ionization cannot be bigger than the first one. That's right. So 3.83 is the answer.
No.
Let's do an example with dilute sulfuric acid. Find the pH and sulfate ion concentration of a 0.0075 molar sulfuric acid solution. And it gives me Ka2. Why doesn't it give me Ka1? Because it's a strong acid in its first ionization. So H2SO4, bless you, will go to H plus HSO4 minus. And that's complete. So if I start with 0.00750 molarity of that, then I'm going to end up with none of this in 0.00750 and 0.00750. There's no equilibrium constant for that. It all ionizes. Now I'm going to look at losing the proton from the hydrogen sulfate ion. This is a weak acid. And we've got the ionization constant here. So we need to put in the information that we know, and we're getting that from the result of the first ionization. So we have no H2SO4 left. It ionized completely to H plus and HSO4. So these are the starting amounts for those substances in the second equilibrium. So this is going to be 0.00750 and 0.00750 and no sulfate. Yes. Wait, why?
Why?
Because this happened first.
No, I get that. Just, I mean, are you saying that those bottom numbers, is that E such as?
This is like
Yes.
start and finish. It's not really an ice table because there's no equilibrium.
Is it like approximately 0? Because we don't really know for that H2SO4.
Well, you could have 0 H2SO4. You just can't have, in an aqueous solution, you can't have 0 hydrogen ions. It's just not possible. That's why it is a thing. I know, you're just pulling my leg, it's fine. So, ice table here. So the change, since we've got 0 sulfate over here, the reaction has to go to the right, so minus X plus X. Actually, I just want to write X and put the plus and X. So then at equilibrium, we have 0.00750 minus X, 0.00750 plus X, and X. Equilibrium constant is 1.2 times 10 to the minus 2. Can we use X as small? Let's write this out in decimal notation. Is 0.012 small compared to 0.0075? No, it's actually bigger. So X is not small here. So I'm going to get out my solver. It's giving me X is 0.0038537. It's getting ridiculous. Is that a valid solution to this problem? If I put X in to this term, do I get something that's 0 or negative? No, I don't. And if I put it in here, I don't get 0 or negative. So this is fine. X can be that value. So that is my sulfate ion concentration, right? And we'd probably want to clean that up a little and say, well, you know, probably 2 significant figures. 3.9 times 10 to the minus 3 molar. And then for the pH, I need the hydrogen ion concentration. And that was 0.00750 plus my X, 0.0038 5, and that's where the significant figures on this one come out. And so I'm going to put in 2 more just to be safe. Uh, 0.0075 plus 0.00385337. And so this is going to be 0.01135337. And if we're going to at least approximate correct sig figs, I think technically this one should only have 2 because the Ka only has 2. So that leaves me with 4 decimal places. That would be the molarity, but that's not what they asked me for. And I'm like, oh, well, what did I do that for? I don't know. Just for fun. So calculating the pH, I want to use that whole number. I don't want to round things. 0.001113. So that, my concentration had 3 significant figures, so then my pH can have 3 decimal places. I did. Thank you. And I thought that 1 was a little squished in there, but there. So that's going to be yeah, the answer is right. I just wrote it down wrong. Okay. Thank you. So that's our pH, and this is our sulfate ion concentration. Any questions? Okay, so finding the concentration of the anions for a weak diprotic acid solution. So we may want to know the concentrations of the anions formed by that polyprotic acid solution, which we kind of did in the last example. But here, if we take our generic diprotic acid, H2X, it loses 1 hydrogen to become HX minus, and then that also loses hydrogen to become X2 minus. And so there are 2 anions here. And sometimes we want to know the concentration of those, and because this is not being added onto something else, we do actually have to consider both of the ionizations. So for HX, we're just going to calculate the hydronium ion concentration like we were going to do for a monoprotic acid, and the concentration of X minus is going to be the same, and then we could subtract from this and figure out what the H2X is if we want that. Then for the X2 minus, we're going to use the HX and the H3O plus that we found in the first one and plug those in here as initial concentrations and then do another ice table. Okay, so this is find the carbonate ion concentration of the 0.05 molar H2CO3 solution in for practice 1717. So let's see if I can go back to that. So this is, the problem we're doing right now is adding on to this problem. But I think that's just going to be more confusing than just doing it from the beginning. So we have carbonic acid, and it's going to ionize and form hydrogen carbonate ion. And we've already done this, but it doesn't hurt to do it again. So our initial concentration is 0.050, approximately 0, and 0. And then our change is minus x plus x, and plus x, so at equilibrium, 0.050 minus x, x, and x. And oh, I see. I put whatever. And then we use the ionization constant to find what am I doing? And this is the one where we found that x was equal to 1.47, or actually 1.48 times 10 to the minus 4.
You said every time we're using Ka2, we're working with acid.
Say that again?
You said every time we're working with Ka2, we're working with the acid.
Well, the Ka1 is also an acid. They're both acids.
So what did you mean by that?
What did I mean by what earlier?
Because you said something about the Ka2, you could tell that it's an acid.
I don't remember saying that.
Strong acid.
Oh, so for the H2SO4, you could tell the first one's a strong acid, and that's why it's not listed. The Ka1 is not listed for sulfuric acid. So this is the result that we got in 1717. We determined that the pH was 3.83, and that's a hydrogen ion concentration like this. So the second ionization, which we did this already, but I wasn't thinking. So now we have a hydrogen concentration that's equal to X and a hydrogen carbonate ion concentration that's equal to X. And so we have 1.48 times 10 to the minus 4, 1.48 times 10 to the minus 4, and 0. I actually got X from taking 10 to the negative pH. I could go back and find the slide with all the writing on it, but it's a pain.
Yeah, I got it.
Okay. And so then the change, and we did this, and I wasn't thinking. There, I said it again. Minus X, 1.48 times 10 to the minus 4, plus X, and X. So that ionization constant, 5.6 times 10 to the minus 11, bless you. And using the X's small approximation to say that X is so small that adding it to this number isn't going to matter, then our X's go away, And then these terms cancel out, and we have x is equal to 5.6 times 10 to the minus 11. Which in the previous problem we said, oh, well, that means we didn't have to worry about it at all. But here it actually has some significance. This is the concentration of carbonate ion. And if that's what we're being asked, then we need to look at this second ionization. Any questions?
So, do we dichroic acid is multiplied?
Yes, a diprotic acid will dissociate into and give off 2 moles. Well, it's not like the bases where they ionize completely and you get 2 moles of hydroxide for every mole of calcium hydroxide. Because these are weak acids, so they only ionize a little bit. The first hydrogen ion comes off, and then there's another equilibrium for the second one. And so most of the time the second one does not contribute worth looking at to the pH. But if we want to know what the anion is, then we have to look at it. Yes? This one's different from the other one because here the question was find the carbonate ion concentration. The previous one,
More work before though, right?
yeah. Yeah, I wasn't thinking.
I know, I'm just making sure I wasn't.
No. So I probably should have just left it alone. See, I get ahead of myself sometimes. Some part of my head says, oh, but I'm supposed to do this. And then like 3 slides later, that's where I'm supposed to do it. So when we did this part in 1717, we were looking at adding this onto the hydrogen ion concentration, and it didn't make any difference at all. And so then in terms of calculating the pH, it doesn't matter. But trying to find the carbonate ion concentration, X is not 0, it is a number. It's very small, but it's a number. Any other questions?
On an exam,
Mm-hmm.
so how do we know if we need to go about doing this step? If it asks for a pH, do we skip it? Do we not do this part, or?
So if you have a diprotic acid or a triprotic acid and they want the pH, then usually you just have to look at the first ionization. When you need to look at the second or third is when you're looking at the anion concentrations. 5.6 times 10 to the minus 11.
And we can ignore the second ionization when it's weak.
Well,
Or just business.
there's only one diprotic acid that's strong. And so, well, it's H2SO4, and it's strong in the first hydrogen and weak in the second. And the only time you have to consider the second, even for that one, is if you have a dilute solution. If it's a relatively concentrated solution, it doesn't matter at all. Yeah. So this is looking at the dissociation of a polyprotic acid. I think this is ascorbic acid, but don't quote me on that. So this has 2 protons here. So in the first ionization, we lose one of those, and we get this ion, and we get hydrogen ion concentration of 2.8 times 10 to the minus 3rd, because they told us that's what it did. And then this ion also dissociates and gives hydrogen ions and the fully naked anion. And so the hydrogen ion concentration given off by this is 1.6 times 10 to the minus 12. The total hydrogen ion concentration is the sum of those. And we see that the second one is so small it doesn't matter. So the amount of hydronium ion produced from the second step is insignificant. So that's a useful thing to remember. The concentration of the anion the fully dissociated anion for the weak diprotic acid equals Ka2, provided that the X's small approximation is valid, which it usually is. And so that's how in the previous example we ended up with the carbonate ion concentration being equal to the Ka. Any questions?